Welcome back to Physics 104B. We're continuing in Chapter 24 on electric current. And in this video, I'm going to cover two sections, 24.3 resistance and Ohm's law, and 24.4 electric power. Earlier in this chapter, you saw the microscopic version of Ohm's law that describes the relationship between electric field and current density at each point within a conductor. Now we're going to look at what we call the macroscopic, and this is usually what Ohm's law is known as. And here it is. It is current equals voltage over resistance. It shows that a given voltage can push more current through a lower resistance. And so, as you can see there, as I've written out in words, that the current through an object is the voltage across the object divided by the object's resistance. Here is an extreme case. This is what's known as an open circuit. It's a circuit diagram. And you've got down on the bottom, it says cell. You can think of that as a battery. And here's a light bulb or something offering resistance. It could just be a resistor, but here it's a bulb with resistance. And right here, the switch is open. This is what's called an open circuit. As we'll see when we get into chapter 25 on electric circuits, we need a closed loop in order for any current to go through. So in this open circuit, with the switch being open, this open switch is a non-conducting gap with effectively infinite resistance. So if you apply infinite resistance to Ohm's law at the top of the screen, you get current equals 0. So we're not going to get any current unless we close that switch, and then we can have current go through. Let's look microscopically, and we're going to relate the microscopic Ohm's law to these new concepts here. So there we've got a wire with the electric field going from left to right, and therefore the current density, or the current goes from left to right, so I'll also say current density vector goes from left to right. And this wire has a cross-sectional area of A, and over the segment of the wire that we're looking at, there's a electric potential difference, that voltage difference, we'll call it delta V. So we'll start with the equation current density is electric field over resistivity, rho. Remember that current is current density times area. So current becomes electric field times area divided by rho. Now thinking about the relationship between voltage difference and electric field, voltage difference is the electric field times the length. And so between the two ends of the segment that we're looking at, we can say that the electric field is the voltage difference. In the picture, I wrote it as delta V. Here, I've just written it as V, divided by the length. So putting all this together, we go with what you see on the top line. Current is electric field times area divided by rho. Here that is electric field times area divided by rho. And I'm replacing electric field with what we've got over here, voltage difference divided by length, right there. And I'm reconfiguring it so it's voltage over, and I'm putting everything down in the denominator. So in the denominator, basically I'm putting the area down in the denominator, so that denominator becomes rho length divided by area. And you compare this with Ohm's law, which is current equals voltage over resistance. And we see this relationship right here, that resistance through the material is the resistivity times the length divided by area. So this is our equation for resistance. Resistance of the material is the resistivity times the length divided by the cross-sectional area. The idea here is that the more length it has to travel through, it's going to meet more resistance. But the wider it is, think about like a pipe that water goes through, the wider the cross-sectional area, the more water you're going to be able to get through. So as area increases, resistance decreases. Now this is for a simple shape like a cylinder. If it's a more complex shape, such as in the textbook, at least in the second edition of the textbook, there's number 61 and number 63. They deal with more complicated shapes. You might need calculus. Let's look at the example in the book. This is example 24.4. It says a copper wire 0.50 centimeters in diameter and 70 centimeters long connects your car's battery to the starter motor. What is the wire's resistance? If the starter motor draws a current of 170 amperes, what's the potential difference across the wire? I've started with the given information. It said 0.50 centimeters in diameter. Let's turn that to the radius. That'll be more important. So 0.25 centimeters radius. There it is, length of 0.70 meters. And it is worth noting that it is a copper wire. We'll use the equation to find resistance. Resistance is resistivity times length divided by cross-sectional area. We need to look up the resistivity of copper in the table in the book, table 24.1, and it says that that's 1.68 times 10 to the negative 8 ohm meters times the length divided by the cross-sectional area. So we're talking about it's a circle, so pi r squared. And you should get 0.60 milliohms. If we want to know what is the potential difference across the wire, so by Ohm's law, voltage, that's potential difference, equals current times resistance. So we take the current of 170 amperes, multiply by the resistance that we got in part A, and we get 0.10 volts. Some applications in everyday life of resistance. One thing they're used for is heating elements, for like a stove or a space heater. Hair dryer, an iron. What happens is this material, the heating element, has a resistance, and so as you run a current through it, it turns the electrical energy into thermal energy as the electrons collide with the ions. And here you see the stove and the space heater, and the element gets so hot that it actually glows red or orange. Also, incandescent light bulbs use resistance. So there you see in this picture, the filament, the electric current comes in one end and it goes through this tungsten filament that has resistance. And so again, it turns electrical energy into thermal energy. It glows very hot, and it glows so hot that it actually gives off visible light. Now, incandescent bulbs have gone out of fashion, and one of the reasons that many people in industries have stopped using them is that they're very wasteful. For the purpose we use them, which is getting visible light, most of the energy actually goes into heat. And so you get a lot of heat out of them, and that also could be a fire hazard. A lot of heat for the light that you get out of it. And so more modern light bulbs are LEDs or a variety of other things instead of incandescent bulbs. And a big practical application of resistance is resistors. So here you see inside a circuit is a bunch of resistors, and we'll deal more with them in a later chapter in this book. But resistors are used for regulating the current inside circuits. Let's look at problem number 49 in the back of the chapter. It's a three-part problem. It says a solid rectangular iron bar measures 0.5 centimeters by 1 centimeter by 20 centimeters. Find the resistance between each of the three pairs of opposing faces, assuming the faces in question are equipotentials. All right, well, it's iron, so we'll need the resistivity, 9.71 times 10 to the negative 8 ohm meters. And again, it's a three-part problem. Let's look at the resistance as we go between the left and the right side. As current goes through, what is that resistance over that 20 centimeter length? We'll use this equation, resistance equals rho length time or divided by area. So we plug in the resistivity. We're going through a length of 0.2 meters. The cross-sectional area, you can look on this right-hand side, you can see it is 0.5 centimeters deep, that's the orange segment that I've drawn, times a height of 1 centimeter, that's the blue segment that I've drawn, so that gives the area. And of course, I've turned them all from centimeters into meters. And you get 3.88 times 10 to the negative 4 ohms, or 388 microohms. If we go between the top and the bottom sides, we're going to use the same equation. We just have to look at it from a different angle. Now, going from top to bottom, there's a length of 1 centimeter. The area that the current goes through is this width of 0.5 centimeters times the length of 20 centimeters. So it's got a much wider area, and it's got a much smaller length than in the previous problem that we looked at. So we get 0.971 microohms, or 9.71 times 10 to the negative 7 ohms. It's much less resistance than when it went from left to right because it's a shorter distance and a wider cross-sectional area. There's a third part to the problem, going from front to back, and so you can do that if you want, and the answer's in the back of the book. But I'll leave that to you as an exercise. The next section is 24.4, electric power. From chapter 22, we learned that the potential difference between 2 points can be thought of as the change in energy, the energy transformed, divided by the charge. So when a charge Q, I'll call it capital Q, moves through a potential V, there is energy transformed, that is Q times V. Now when I say energy transformed, something dealing with energy happens, and we've seen examples where kinetic energy might be gained, it might be lost, potential energy might be gained or lost, but something happens with transformation of energy. Now, if you put a potential difference across a resistor, a current flows through it, and the quantity V is the energy gained per unit time as the charge falls through the potential difference. In a resistor, that energy is dissipated through collisions, and that heats up the material. So V is also the energy per unit charge going into heating. We have power equals the energy transformed, so QV over T. And let's separate those out, Q over T times V, and that becomes power equals current times voltage. Now, we can think of that as power dissipated as heat in a resistor, but it works anytime electrical energy is being converted to some other form. So for example, if we measure so many volts across an electric motor and the current going through it, then we can say that the motor is converting the electrical energy to mechanical energy based on this equation. And we'll go over some examples of that. So power dissipated in heating resistor as the charges fall through the potential difference, V is P equals IV. And here's an example. Let's say the example I just gave, we have 5 volts that's across a motor, and 2 amps is the current going through the motor. Then power equals current times voltage. We'll just say 2 amperes times 5 volts, and we get 10 watts. So we're getting from this motor 10 watts of mechanical power. Now, P equals IV, a very useful equation, but sometimes it's also useful to not involve V, or maybe involve resistance. And so we can substitute in using Ohm's law. Here are other versions of the same equation. If you take voltage, go up to P equals IV, and recognize that voltage is I times R, then that becomes P equals I times R. So we get P equals I squared R. Another version is P equals V squared over R. So on this page, there are 3 equations for power. They all say the same thing, but it just depends on which one you want to use, depending on, are you given I and V, are you given I and R, or are you given V and R? Let's do another example. Let's say we have a current through a 10-watt light bulb, and it's getting 120 volts potential difference, and I want to know, what is that current? And let's figure out the bulb's resistance while we're at it. We can say the current is P over V, 10 watts divided by 120 volts, and we get 0.0833 amps or 83.3 milliamps. If we then want to know the resistance, we can say resistance is V squared over P, using one of those versions of the power equation. 120 volts squared divided by 10 watts, and we get 1440 ohms. Or another solution, you could use Ohm's law, which becomes resistance equals V over I. So 120 volts divided by 0.0833 amperes, and you get, again, 1440 ohms. Let's look at problem number 53 in the back of the chapter. It says a 100% efficient electric motor is lifting a 15 Newton weight at 25 centimeters per second. How much current does it draw from a 6-volt battery? Now that might not be realistic, 100% efficient electric motor, but they're doing that just to keep the math easy and not to worry about the efficiency. The idea here is that all of the electrical energy goes into mechanical energy. I've written down the given information. The weight that it's lifting is 15 newtons. It's lifting it at a speed of 25 centimeters per second, and the potential is 6 volts. Well, let's think about from last semester, just the idea of the power in lifting something. Power is work over time. And if we're lifting a weight up some height, then remember that work is mg times the height difference, the change in height. And then we're dividing by time. Now I'm going to separate out those parts, put mg to the side, and we've got in parentheses delta y over t. And the reason I've done that is because that's the speed, 25 centimeters per second. Now we have the weight, that's mg, 15 newtons, times 0.25 meters per second, and we get a power of 3.75 watts. So that's the mechanical power that the motor's doing. We're going to use this 3.75 watts and now relate it to the electricity. So there it is again, what we did on the previous screen. Now let's think about the electrical aspects of this problem. Power equals current times voltage, which means current is power divided by voltage. Therefore, we get current equals the power we got with what the motor is lifting, 3.75 watts, divided by the voltage, 6 volts, and we get 0.63 amperes. A metal's resistivity or conductivity, remember those are just reciprocals of each other, is dependent on the temperature. Thermal speed increases with higher temperature, and that means there's an increased collision rate between the electrons and the ions. And that means there's increased resistivity and increased resistance. There is a nearly linear relationship between resistivity and temperature. Now, one application of this is incandescent light bulbs. The filament when the bulb is on is thousands of Kelvin. But when the light bulb is off, it's room temperature and resistance is much lower. Now, incandescent bulbs aren't used that much, but a common occurrence when we all used incandescent bulbs was when a light would blow out. And the light would always blow out, a light bulb would just blow, when you're turning on the light. It was very rare that you'd just be sitting in a room with the light on and suddenly the light bulb blow. It would always happen when you turn on the switch. And the reason is that that's when the resistivity, and therefore the resistance, is much, much lower. And if you think about Ohm's law, current is voltage divided by resistance. If resistance is very low, then that's when the current is very high. So the light bulb had the greatest current going through it while it was at room temperature. So if the bulb is weak, the filament is weak, and it's on its last legs, it's very fragile, it's about to break, the thing that sets it off is running a high current through it, and that's right when you turn it on, well, while it's cold. That is the end of section 24.3 and 24.4. Have a great day.